Today's topic is inverse functions. So far we've discussed functions in detail. Today we're going to focus on inverse function. First, let's look at this idea that what type of functions have inverse and what does the inverse do. There is something called the one-to-one property. One-to-one property is, let's assume you're given a function f. If you remember, pick points from the domain, the outcome is in the range. The input and output, this is the domain and range. For example, if you have the points 1, 2, and 3, and I ask you f of 1, you should say 5, because the arrow points toward 5. F of 2 would be 5, f of 3 would be 6. And for every x value, you have exactly one y value. If I pick x equal to 1, for example, I do not have two outgoing arrows. There is only one outgoing arrow, and it approaches to one specific value, in this case, y equal to 5. Now, we're going to discuss an inverse function. Inverse function means look at the arrows backward. What if I don't give you the x value? What if I give you the y value? Can you tell me originally what the x value is? In this sense that if I give you the y values, can you tell me what were the original x values? This is what we're looking for, and we write it as f inverse. This -1 is it's not like 2 to the -1. 2 to the -1 means 1/2. F to the -1, that -1 is just a part of the notation. This means inverse of f. Inverse of f. It's just a notation. So it doesn't mean that 1 divided by f. F inverse, this does not mean 1 divided by f. This is not correct. Okay. This is just a notation that means going backward in the f. So here, for example, if I look at the range and pick 5 and 6 and ask you, what is the corresponding x value if I pick y equal to 5? You'll say either it should be 1 or it should be 2. Because if we look at the 1 and 2, they both give you the y value of 5. So the original x value must be either 1 and 2. So now, if I ignore the inverse notation and say start with 5 and approach 1 or 2, then if you call this a G map, this G is not a function, because for one input you have two different outputs. It means the outgoing arrow is two outgoing arrows. There are multiple outgoing arrows. So to have an inverse as a function, you just need to have one outgoing. You cannot have two arrows outgoing. So this causes one relation for a function to have inverse. It means if I pick an x value, I should have one y value. To have an inverse, for every y value, you should have exactly one x value as well. You cannot have two outgoing the other direction either. Otherwise, it would not be a function. So this is what we call a one-to-one. That means every x you pick, there is a y value. Every y you pick, there is an x value, not multiple. In this case, this f here is not an one-to-one function, so it doesn't have an inverse. One-to-one is just in the sense that for every x you have one y, if for every y you have one x, not multiple. If you draw the mapping, there's always one arrow from one point to a different x, different y, something like this. None of the x and y's are equal to each other. Okay, this is what the one-to-one property means. Here, similar to vertical line test, we have a horizontal line test that just shows that if you have a graph of a function, can you say if that function has an inverse or not? Remember, these are functions because it passes the vertical line test. Horizontal line test tells you if the function is one-to-one or not. Meaning, if I pick an y value, for example, if you pick this y value, let's say 3, do you have 2 points with that y value on the graph or not? So in this case, if you look at these 2 points, they both have coordinate of 3 as their y coordinate. X values could be 1 and let's say -2. So you have 2 points, 1, 3, and -2 and 3. That means when you draw the arrows from 1 and -2, they both end up at 3. So the inverse is going to give you two outgoing arrows from the same point. That means the inverse is not a function. So What type of functions have inverse? The ones that if they pass the vertical line, they should pass the horizontal line. That means horizontal line cannot cross multiple times. It only crosses at most once. For every horizontal line that you draw, you can only cross once. In this case, for this example, if you draw this line, you cross the graph multiple times. So this, even though it's a function, but it doesn't have an inverse. No inverse. Because it's not a one-to-one function. Every horizontal line crosses multiple times. In this case, there is a horizontal line that crosses multiple times. If you look at the other example, now here, any horizontal line that you draw, it crosses once. So this is a one-to-one function. This is a notation for one-to-one function as well. It means in each direction, if you look at horizontal line or vertical line, they both give you a function. The original is a function, the inverse is a function as well. So this has both f and f inverse are functions. That's what it means. F inverse exists. Sometimes this, if you look at the first example, sometimes you can restrict the graph to make it inversible. You can restrict the graph by saying, okay, let's cut off some pieces of the graph. Only look at this part, up to a certain section, up to here. This way, now this graph passes the horizontal line test as well. Sorry about that. Let me erase this. Yeah. So now if you ignore the left half of the graph and only consider the right half, this right half passes the horizontal line test. So half of the graph actually has an inverse. So I can say, I'm going to discuss the inverse only for half of the graph. This happens normally for quadratic functions. So we will get to that, but it's just an idea to know that by restricting the graph in the domain, if I say the x's are not allowed to go less than, for example, -1 or less than 0, then the graph is the function is one-to-one in the right half. Therefore, I can discuss the inverse. I'll show you an example in a bit, but just the idea of horizontal line test is important. Okay, inverse function. Notation, again, f inverse of x, just a function. This -1 is a part of the notation. That means the inverse. As we started originally with the function, we said it's a set. So, for example, function f contain 1, 2, -1, 3, and 4, 0. These are a bunch of points. And here is the graph of f. This is the graph. 4, 0, 1, 2, and -1 and 3. So what does the f inverse look like? F inverse means you're given the y values as an input. So as an input, I'm given 2, 3, and 0. And I want to figure out what is the x values. The x values would be 1, -1, and 4. So the relation between f and f inverse is basically x becomes y, y becomes x. You only interchange the x and y's. The inputs are in other order. So if you graph the f inverse, let's graph the f inverse as points 2, 1. Where is 2, 1? 2, 1 would be here. 3, -1, 3, -1. This is 3, -1. And 4, 0 becomes 0, 4. So here is 0, 4. If you look at these points, let me highlight, for example, these two. If you look at these two, what is the relation between those two is their reflection of each other about a specific line. Let me draw that line. You might be able to guess it. It's the 45-degree line. This dashed line. I don't know if it's clear or not. Maybe I should have used a different color. That's not helpful. Okay, let's try blue. Okay. So here, if you look at the 45-degree line and compare these 2 points, they're symmetric about that point. What if I compare the other 2 points? What if I compare these two? This is -1 and 3 and 3 and -1. They're exactly symmetric about that line as well. How about the other 2 points? They're symmetric as well. 4, 0, 0, 4. So if you're given a graph of f, let's say you're given this graph of f, and let's say you see this graph and say this graph passes the horizontal line test. That means it has an inverse. Then draw the 45-degree line. I could draw that line better. There. Then what would be the graph of the inverse? The inverse is exactly, you reflect every point. That points become here. If you pick this point, that point go there. This point comes here. That point goes there, and so on. All these points, they will reflect it. So what you get is this reflected graph. If this is f, this must be f inverse. All the points are reflected about this 45-degree line, every point. All those points are reflected. If the graph had, let's say, the left-hand side as well, like quadratic, it would not pass the horizontal line. Now, if you reflect this whole graph, let's reflect this part as well. What would you get is that. If you reflect the other half, if you reflect this left-hand side, what you would get is exactly that. Now, if you look at this graph and say, is that a function? The answer should be no, because it does not pass the vertical line test. That's why we have the one-to-one property. That's why originally we don't have this left-hand side, so we can have the graph as a function. That's why we restrict the graph. That normally happens when you have x squared functions. And if you think about it, this is x squared. What does the other one look like? The other one looks like square root of x. And in some sense, they're inverses of each other because they do opposite operation. If you pick 3, raise it to power 2, you get 9. If you take a square root of 9, what you get is 3. It's an opposite operation. Okay, so the inverse function, it means basically the input is y, the output is x. The range and the domain will be in opposite order. Okay, here is an idea of how to check if two functions are inverses of each other. It's not complicated, it's very easy. Let's say start with the function f. We discussed something called composition, but I want you to see this. Let's say you're given an input x, and through f, what happens to that point? We go to a specific point y. Okay? Through f inverse, what does f inverse do? F inverse starts from y and takes you back to the original x. So if you start with x, go through f, then go through f inverse, what happens is you will end up exactly at x, at the starting point. That means if you compose f inverse and f, doesn't really matter where you start with, you'll end up at that location. If I start from this x or this different x, where do I end up is exactly at that location. If I start from x, I will end up at x. The same with f inverse. If you start from here and go through f inverse, then come back, where do you end up is at the starting point. So at the starting point, if we call it x, where do you end up is again x. The order of the loop does not matter. It only matters where you start with. So what we say as if two functions are f inverses of each other, then means their composition of f with f inverse must always equal x. Assuming the x is the input. If you call the input y, z, whatever, then the result should be y or z. So this is an important thing to know. Composition of f with f inverse at x equals x. Composition of f inverse with f at x is still x. And we normally use this to check if two functions are inverse of each other. Here's an example. Given two functions f and g, you want to figure out is really g the inverse of f or not. So what do? We calculate that composition. Let's figure out what is f of g. Remember this f of g of x or f of g of x. This was f of g of x. That's the same meaning. If g is the inverse of f, then this should end up x to be x. So what is g of x? G of x is 2x minus 1. I don't know what f is at the moment. I know, but g is 2x minus 1. So I replace g with 2x minus 1. Then replace 2x minus 1 into the function f. Into the function f, instead of x, you replace 2x minus 1. So what you get is 2x minus 1, here plus 1, then divide by 2. What you get is simplify. Negative 1, positive 1 will cancel out. 2x divided by 2, simply x. So what we got? Composition of f and g, x. Is that enough for us to say g equals f inverse? Not really. You have to compose the other way as well. You have to calculate g of f to see is that even really true as well. Sometimes the idea is only one-sided. So it's not true in both directions. That way it means that g and f are not inverses of each other. So f is given x plus 1/2. What is g of x plus 1/2? Replace x plus 1 divided by 2 into g. 2 times x plus 1 over 2 minus 1. These two will cancel out. X plus 1 minus 1, simply x. What did I get? Composition f and g equals x in both cases. So what can I say? F and g are inverses of each other. So I can say basically f inverse of x equals 2x minus 1. Or you can say g inverse of x equals x plus 1 over 2. It doesn't really matter which way you want to mention it. One is the inverse of the other. Okay, how about this example? Is f and g, is g the inverse of f or not? So let's try to calculate FOG. FOG of x. Let's say what you get is f of square root of x plus 1. Square root of x plus 1 goes in for x into the f function. So you get square root of x plus 1 squared, then minus 1. What does that simplify to? Square root of x plus 1 squared is simply x plus 1, then minus 1 equals x. So I got FOG equals to x. How about g of f? This is g of f is x squared minus 1. What do we get is square root of x squared minus 1. Then there is a plus 1. Square root of x squared. Is that equal to x? This is the question that I want you to answer. If you say at this point, this equality is true, then you might say x equals to square root of x squared. In some sense, this is true, but not always. So here, before this equality is not a true statement in the moment, but I want to show you why it's not a true statement. I wrote equal, but I want you to see it. Let's say square root of 3 squared. Is that equal to 3? This is what we want to figure out. The answer is yes. Square root of 3 squared is 9. Is it equal to 3? Yes, it is. How about square root of negative 3 squared? Is that equal to negative 3? In this case, the answer would be not really. Square root of negative 3 squared would be 9. Square root of 9 would be positive 3. So this equality is not true. This is a true statement only if x is positive. So this equality is not really x. It's equal to absolute value of x because you want the outcome to be positive. So what is the composition of g of f? It's not x. It's absolute value of x. So what does it tell me? It tells me that f does not equal to g inverse. F inverse does not equal to g, or g does not, or f does not equal to g inverse. Not equal. Because at the end we didn't get x, we got absolute value of x. The outcome has to be positive. It's never negative value like negative 3. In one sense, you can see it through the graph. Here's f. How does f look like? X squared minus 1. X squared is parabola minus 1 shifted down 1 unit. is x squared minus 1. Is f 1 to 1? Not really. Draw a horizontal line. It crosses more than once. Here 2 points. So what does it tell you? It tells you that f does not have an inverse. So this, if f does not have an inverse, it's not possible for f and g to be for g to be the inverse of f, because f is not supposed to have an inverse. But here's the important part. But if I ignore this left-hand side of the graph and only focus on the right-hand side, if I say let's restrict the graph to only x's that are positive, all the x's that are greater than 0, then what can I say about f? Does f have an inverse? Yes, it will. Then what can I say about the absolute value of x? What is absolute value of a positive number? Absolute value of a positive number would be exactly the same as itself. Absolute value of 3 would be 3. Absolute value of 5 would be 5. Doesn't really matter. So if I make this restriction, then say x is greater than 0 or equal, then this absolute value would be exactly x. Then what can I say? I can say f and g are inverses of each other in that case, because f can have an inverse, and that inverse turns out to be exactly square root of x plus 1. You can check it by calculating, for example, f of 2. Pick a positive number, replace it into f. What do you get is 2 squared minus 1. 2 squared minus 1. This is 3. Now, ask yourself, if I calculate g of 3, do I get 2? If I get 2, that means if you start from a y value, do you get the x value? If I get 2, that's kind of like the whole purpose. So how do we calculate g of 3? Square root of 3 plus 1. What do you get is 2. And you see that you start with 2, you got 3. So if you start from 3, what do you get is 2. Means you're in that loop of starting from 2, you go to 3. Starting from 3, you'll go to 2. That's what the loop is. So it's important that if we make this restriction, we make the function 1-to-1, then we can discuss the inverse for it. So normally for quadratic function, there is this extra restriction, just to make sure that the function is 1-to-1. And the whole idea of how to find the inverse functions, this is the general case. I don't want to break it up into specific cases. So to find the inverse function, you do these certain steps. If you're given the function f, replace f of x with y. So say y equals to f of x. As if we know, what do you want? You want to have x and y interchange. That means replace x's with y's, y's with x's. That's the whole purpose of the inverse. You start from y, you go back to x. So we want to interchange the x and y everywhere. And we want to solve for y. After that, call it f inverse. That would be the inverse function. We'll do examples, but these are the main 4 steps. This first and last step is just for the notation. The middle step, replacing x and y, and normally you have functions in terms of y. That's why we solve for y. So here's an example. Find the inverse function for this, f of x equals 3x minus 5. I'm going to do the steps. Step 1, y equals 3x minus 5. Replace f with y. Step 2, replace x's and y's. Y replaced with x, x replaced with y. Step 3, I want to solve for y. So move everything to one side, isolate y. I'm going to do this, x plus 5 equals 3y. So what is y? X plus 5 divided by 3. This is step 3. Step 4, replace that y with f inverse. Call it f inverse. X plus 5 divided by 3. That's it. There's nothing complicated about it. As long as you can follow these steps, you can always figure out the function inverse. The only important thing is that you just need to be careful that the function that you start with, this original function, is 1-to-1. That means it has an inverse. Otherwise, you might end up with, you might have difficulty solving for this y at this stage. Okay, here's another example. 2x squared minus 3. as I said earlier, parabolas always cause issue. 2x squared minus 3. This is 2x squared minus 3 shifted down 3 units traced along the y, so something like this. This is 2x squared minus 3. I don't really need to figure out exactly. And you will see that this is not a one-to-one function, so it doesn't have an inverse. So I'm going to restrict the function, and I say, let's assume all the x's are positive or greater than 0. That means the graph does not have this left-hand side. It's only having the right-hand side. X positive means this is only the domain allowed to be on the right-hand side, nothing less. Okay. I'll show you both cases, x positive or x negative. If the restriction was x less than or equal to 0, what would you do? You will see that there is only a small difference. Okay, so let's try to figure out what is the inverse function. Change this to a different color. Okay, first step, y equals 2x squared minus 3. Second step, step 1. Step 2, interchange x and y. X equals 2y squared minus 3. Step 3, solve for y. So add 3 equals 2y squared, divide by 2. Y squared equals x plus 3 divided by 2. What is y? You should take a square root from both sides. If I take a square root from both sides, what do I get is square root of x plus 3 over 2. Remember, when you take a square root from both sides, you should always consider the plus or minus, right? So there is a plus or minus out here. And this is the reason why f does not have a unique result. That's why if you consider both left side and right hand side of the f, then you would have this plus or minus. You would say, which one do I want? Do I want the positive x values, or do I want the positive y values, or do I want the negative y values? This is how this restriction x greater than 0 or x less than 0 applies. If you want the positive ones, then I'll say, okay, let's ignore the negative because I have this restriction of x greater than or equal to 0, so I do not pick this negative. The y values are supposed to be positive. So what is the inverse? F inverse of x is simply square root of x plus 3 divided by 2. If it was the other case, then at the end, step 3, you should get negative square root of x plus 3 divided by 2, because we assume that the x values are negative. So if the x values were negative, then the y value means the y value outcome have negative value as well. This is just based on this simple restriction. If you reflect these sections, each section separately, so for example, if I reflect this part, what do I get is something like that. And this is for the first case. What do you see is y values are positive. If you had the left-hand side of the graph, if you had this left-hand side, and you reflect this left-hand side, what would you get is that. And what you have here is y negative. That means depending on which section you pick, depending on if I pick this left-hand side or if I pick the right-hand side, I will have two different options, y less than 0 or y greater than 0. All this is just these two specific restriction applies just because the original function was not a one-to-one, so you had to break it into two sections. Normally, they already tell you what the restriction is. So f inverse of x, in this case, we have negative square root of x plus 3 over 2. Okay, this happens only when you deal with second degree or fourth degree or sixth degree, the even degrees of polynomial. Okay. And sometimes there is combination of cubic and second degree, but it never happens on linear. Linear, if you have a straight line, it's always one-to-one. There is no reason to break it up and say left-hand side works this way, right-hand side. It's a one-to-one everywhere, so there is no restriction. Cubic by itself, if you remember a cubic function, cubic has this general shape, unless there is a combination with quadratic, then in that case there would be something like this, then you do not pass the horizontal line test. That would be more complicated. So generally, if you have simply x cubed minus a constant, this is how the shape looks like. So it's a one-to-one function, so you do not need to break the cubic function at all. Okay, here's an example of a cubic, and you want to figure out the inverse. So in all these examples, we're looking for the inverse. Again, y, replace y with f with y, x cubed plus 2. Interchange x's and y's, so x equals y minus 3 cubed plus 2. What do? We solve for y, so I subtract 2. Let me do this step by step. X minus 2 would be y minus 3 cubed. How do I get rid of the cube? You take a cube root from both sides. Cube root of x plus 2, x minus 2, equals cube root of y minus 3. Here's the difference between cube and square root. For cube, you do not need the plus or minus, because you can have positive or negative numbers inside this cube. Cube root of negative 8 makes sense. Negative 2. It's a real value. There was no need for plus or minus. So there's a cube here, sorry. I forgot. So now I can say these two will cancel out. What do I get is cube root of x minus 2 equals y minus 3. So what is y? Y equals cube root of x minus 2 plus 3. Add 3 to both sides. So what is the inverse? Cube root of x minus 2 plus 3. So what was the important stages after you interchange an x and y? This is the important stage. Make sure that you solve this equation. Sorry, this is the original equation here. After the interchange, make sure that you isolate for y correctly up to this point. After that is just notation. Before that, just notation. Okay. You can always double check your work. For example, calculate f of 1. See what do you get. F of 1 for the example here would be, let's pick 1. 1 minus 3 is negative 2. Negative 2 cubed is negative 8 plus 2. You'll get negative 6. If you replace 1 into the function f, you'll get negative 6. At the end, if you replace negative 6 into the function, you should get 1. Otherwise, you've made a mistake. So let's try this. Negative 6 minus 2 cubed plus 3. What do you get? Cube root of negative 8 plus 3. This is negative 2 plus 3. What do we got? Positive 1. So here, if you compare, you put 1 into f, you get negative 6. If you replace negative 6 into the inverse, what do you get is 1. You're going backward in the loop. Okay. This is just important to check. You can check by numbers. You can go through your process one more time. You can do the composition. Composition is the correct version of checking, but you can always check with numbers as well. Okay, here's one example that you start with cubic, and we want to figure out the inverse. Again, all these examples, there is nothing new to it. It's only how you isolate y. That's the important part. First step, then second step, replace y with x. Cube root plus 1. And then, by the way, if it was square root, you will do the same thing. Square root already has the restriction applied to it. So how do I isolate? Subtract 1. Do not cube it right away. First get rid of this 2. Divide both sides by 2. X minus 1 divided by 2 equals cube root of y. Now you can cube both sides. Raise both sides to the power 3. What you get is y, because these two will cancel out, equals x minus 1 divided by 2 cubed. So f inverse of x is x minus 1 divided by 2 cubed. Okay. Nothing new to it. It's only the same steps, you're just applying it to a different type of function. We will use this same idea for exponential, logarithmic. If you do trigonometric functions, exactly the same thing. There is nothing new about this. If you remember how we solved inequalities for polynomial, it didn't really matter what type of polynomial it was, as long as you could do the steps. So the same thing with inverses. As long as you can follow the steps, it doesn't really matter what type of function it is. It has to have an inverse, then you can go through these. Okay, I think this is good enough for this topic. Try a bunch of examples, do the homeworks. Let's continue this next time.